not can recall.
This call is now being recorded.
What did you say?
This call is now taking notes.
You didn't respond. I said, have you come across moment of a force as a topic in physics?
Yes.
Okay.
Yes.
What about you? Okay. Okay. Now, what exactly, how do we define the moment of a force? Can you recall? Are you forgotten?
I can't recall.
Okay, that's fine. That's fine. Now, let's just go straight. Now, the moment, when we talk about moment of a force about a point is defined as the turning effect of the force about that point. So, we define moments. Moment of a force is the turning effect of a force about a point. And that is simply what moment is. The turning effect of a force about a point is called moment. It is given as a product of the force and the perpendicular distance. So mathematically, or let me write that first, it is given, I wouldn't be doing all this right there. It is given as the product of the force and the perpendicular distance. When we say perpendicular, what does that even mean? When we say perpendicular distance, someone should come to the rescue. Victoria, yes.
Jesus. Perpendicular. Are you talking about a line?
Yes, you can define perpendicular in terms of a line. But when we say perpendicular, what exactly is perpendicular? Two things are perpendicular if what? What about you?
That means perpendicular means a line resting on a straight line.
Okay, I get what you're trying to say. It's a line resting on the straight line. How do you mean resting? Okay, but that's fine. Now, in a nutshell, not to take more time, not to take further time, two things are perpendicular when the angle between them is 90 degrees. For example, let's say I have a line being drawn this way. I have another line falling this way. Now, the angle between them, as long as it is 90 degrees, we say that this line and this other one are perpendicular. So notice that in moment of a force, we say that it is given as a product of the force and the perpendicular distance. It means that before we can resolve our moment, we have to consider that the angle of inclination is 90 degrees. And if the angle is not 90 degrees given, so we have to resolve it into 90-degree angle before we can proceed with our calculation. So mathematically, this is how we write the formula. The moment of a force M is equal to F times D, where F is the force and D is the perpendicular distance. So this is how we write moment. And then, of course, I said, if this distance is not perpendicular, if the force is not perpendicular to the distance, it means that we can write the moment of a force. So let's say at angle theta, or let me write, if the force is inclined at an angle theta, if the force is inclined at an angle theta. Let's call that angle theta. So it implies that our moment of a force M can be given as F times distance, then multiplied by the sine of the angle theta. So this is how we do it. So meaning that if they give you an inclination that is not 90 degrees and you want to resolve the moment, you want to find the moment of the force about that point. So you're going to consider the product of the force and the distance alongside the sine of that angle. So F times D multiplied by the sine of the angle of inclination then will give us the moment of that force. For instance, let's say I have I'm trying to resolve the moment about this point P, and then I have an angle here. Let's assume that this angle is 30 degrees, and then I have my force. Let's say this force is like 2 Newton, and I want to find the force about this point. And then if I consider, I'm simply going to consider that this force, let me call it M, is going to be FD sine 30 degrees. So that's how it is. So you have to consider the angle of inclination alongside the distance and then the force. So their product gives you the moment about that point. Okay, so that's just that for that. So that's simply what moment is. Also, you can consider moment as a torque. So sometimes you can see they wouldn't ask you to define moment, they'll ask you to define torque. So whether they mention torque or they mention moment, they are basically saying the same thing. So torque is also the force about a point. The same way moment is defined as the force, as the turning effect of a force about a point, we also define torque as the turning effect of a force about that point. You understand that? So they are basically the same thing. Okay, now another thing you have to know is couple. So we have couple. I want us to define some few terms before we go straight into some things that really matters on this topic. What exactly is couple? How do we define couple? Who can help us? Since we have just you and Obaomi, that's Victoria, you and Obaomi in the class, so I'll just be calling two of you. So tell me, Victoria, what is couple? Victoria, how do we define couple? Okay, Obaomi, come to the rescue. How do we define couple?
I don't know, but let me just try. Can I define couple as something two things that are joined together?
Of course, two things that are joined together. That's correct, but that's not correct in this context. That's not absolutely correct in this context. Even though a couple has to do with two things, you're correct on that. So we simply say that a couple is a system of two equal but oppositely directed forces that is not acting on a straight line. So a couple is a system, take note, a couple is a system of two equal but oppositely directed forces So a couple is a system of two equal but oppositely directed forces that are not acting on a straight line. So not acting on a straight line.
Please, your network is breaking. Can you come again with the definition?
Okay, I said a couple is a system of two equal but oppositely directed forces not acting on a straight line. Two equal but oppositely directed forces not acting on a straight line.
Okay.
So that's what a couple is. Now, imagine what exactly does this even mean? When we say a system of two equal but oppositely directed forces. Now, let me try to sketch a diagram. Now, let's say this is usually a diagram we use to illustrate a couple. Now, I have a force acting on this direction. I have another force acting on opposite direction. Now, these two forces, for them to be a couple, they are actually equal in magnitude. So if the force here is 4 Newton, automatically this force also here is 4 Newton. The only difference is that they are acting in opposite direction. That is it. And we can see this application of couple by when you try to turn the your tap, you try to open your tap. Now you notice that you open the tap on this direction. Or let me use a more practical example, something you can relate with. Now, if you have ever turned a handle of a door, so you try to push the door downward. So as you're pushing the door downward, now you notice there is a hinge inside the door that pushes upward. So the handle is going downward, but the hinge of the door is pushing the door upward, which is actually what happened before the door opens. So if what is required to open that door, if the effort or the force that should be added on the handle for the door to be open is about 4 Newton, if anything less than 4 Newton, the door is not going to open, which is the reason why a child, sometimes you see a child on the door, the child try to pull the handle of the door doesn't respond. The reason is because that child is not able to apply a sufficient force that would cause the hinge of the door to be pulled in the same direction, because in opposite direction, because the force applied determines what the opposite force would be. So if I'm pulling the handle with a force of 4 Newton, the hinge also operate with the same magnitude, only moves on opposite direction. So that is exactly what a couple is. A system of two equal but oppositely directed forces that are acting not on a straight line. That are not acting on a straight line. Of course, you can see that if I try to draw a line here, so this guy is pointing on this direction, this guy is acting on another direction. So they are not both acting on the straight line like this. They are acting not on a straight line. So they are equal in magnitude, they are moving on opposite direction, and they are not acting also on a straight line. And many a times you might be asked to find how do you calculate the moment of a couple. So it means that for us to even calculate the moment of a couple, we need to know what the moment of a couple is, which brings us to the next heading. But I only gave one illustration of one application of couple. Another application can also be let's say turning your car steering can be an application of couple. Turning your tap, I've said that, can be an application of couple. So try to pull down the handle of a door is also another application of couple. So all these things I mentioned now, we create a system of two equal but oppositely directed forces that are not acting on a straight line. And those are applications of couple. Just in case you come across a question that states 3 applications of couple. So you can easily say that. So let's look at moment of a couple. Now we know what a couple is. What is moment of a couple? So you've known a couple and you've known moments. So we can now join the two together and get the moment of a couple. So who can help me to explain moment of a couple? Anyone? Okay. The moment of a couple is the product of one of the forces and the perpendicular distance between their line of action, between the line of action of those two forces. So the product of remember we say moment can be given as what? The force applied multiplying the perpendicular distance. So in this case, moment of a couple is then defined as the product of one of the forces and the perpendicular distance between the lines of action of those two forces. I repeat, the moment of a couple is defined as a product of one of the forces and the perpendicular distance between the lines of action of those two forces. Just like I drew before, now let's assume that this is my couple system. I have a force pointing upward. Let's call that force F1. So I have another force pointing downward. Let me call the force F2. Now I have their distance of separation. Let me call that D. So for this to be a couple, remember that moment is equal to force times distance. So therefore, and you know that these two forces are equal in magnitude and direction. So the F1 is equal to F2. So anything the F1 is equals to what the magnitude of F2 is going to be. Therefore, we can now take the moment of a couple as F1 multiplying their distance of separation, which is also equal to F2 multiply their distance of separation. So this is what a couple is. The moment of a couple, the product of one of the forces. Notice that these forces are perpendicular to the distance of separation. So you can see that this line here, the angle that is being subtended from the force to the line of action is 90 degrees. And also from this point to here is also 90 degrees. And that is why I said it is the product of one of the forces and the perpendicular distance between the lines of action of those two forces. And that is exactly what moment of a couple is all about. So the same way you can find your moment F times D, this one is also F times D. The only difference is that in couple, we have two forces that have the same magnitude, but they are moving in opposite direction. So if you consider one of the forces multiplying that perpendicular distance, that would give us the moment of a couple of that system. And that is what we are talking about. Okay. So let's move on. Meanwhile, does that make sense? Does anyone have a question? Melody, you just joined the class now. And I'm sure you're following. Okay. She didn't respond. So let's move on. Oh my goodness. Okay. So let's move on. So the next thing we've talked about moment, we've talked about couple, we've talked about the moment of a couple. The next thing I want us to talk about is the principle of moments. The principle of moments. Principle of moments. The principle of moments. Now, anytime you are being given a question on moments, you must always recall the principle of moments, because every question always makes use of this principle. It doesn't matter the question given to you, you can always work out the problem using the principle of moment. And what does the principle of moment say? This principle says that anytime a body is in equilibrium, whenever a body is in equilibrium, that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. That's what the principle says. So I repeat, the principle states that if a body is in equilibrium, let me write it. This states that if a body is in equilibrium, of course, you know what equilibrium means. Is if a body is at rest. That's what I mean by that. If a body is in equilibrium,
So I can't see your screen, Mo. Cannot see your screen.
oh my God. How come? What happened?
Don't know.
Is that so for everyone?
Yes.
What about now?
Yes, you can see it now.
Okay, I was trying to explain the principle of moments. And I said the principle says that if a body is in equilibrium,
Yes.
the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. The sum of the clockwise moments, if a body is in equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moment. That's what the principle is saying. So anytime for a body is at rest, this principle says that the moment moving on the clockwise direction is equal to the moment on the anti-clockwise direction. And when we say clockwise, what does that even mean? Clockwise means that, now let me assume I have a beam. Let me draw a beam, something like this. And then I have this to be my points. This is the point of moment. Now I have a force acting on this direction. Let me call this F1. And of course, the distance from here to the pivots, let me call that D1. And then I have another force acting on this direction. Let me call this F2. And then the distance from here, where the force is, to the pivot, I can call there D2. So if I consider this motion, this is my clockwise about that point, because if I consider from this point, this object, this beam is going to move on the direction of the clock. So you can see that if I tilt, if F2 happens to be bigger than F1, this beam is going to swing in the direction of the clock. It will swing in the direction of the clock. But assuming F1 is bigger than F2, then it means that this beam is going to fling anti-clockwise. So it will move from right to left. It will not move from left to right. Remember, a clock turns round from left to right. So that is what I mean by clockwise direction. And according to the principle, he said that assuming this body is at rest, that the sum of the clockwise moment, in this case, I only have forces, one force on both, two forces, one on both sides. So it means that my moment, which is F times D, so F1 multiplied D1 is equal to F2 multiplied D2. And this is what the principle says. So for this thing to be in equilibrium, the product of the F1 and the D1 must be equal to the product of F2 and D2. Remember that moment is force times perpendicular distance. And of course, these forces are perpendicular. They are not inclined. The angle between them and the distance is 90 degrees. And the line of action is 90 degrees. And that is what we are saying. And that is simply what the principle is all about. Okay. Now, the next thing I want us to look at is the center of gravity. I'm trying to use this, I'm just picking out points. These are salient points. I'm picking out salient points so we can quickly go into problem solving. I wouldn't want us to do so many things without solving questions, because if we don't solve questions, it will end you some confusion when you're trying to do them yourself. So center of gravity. But these things are few things that you might come across in your exam. So they are very important also. So has anyone here come across the word center of gravity? If yes, what does that even mean? I have Melody in the class. I have yes. Anyone who is speaking? About me, I'm listening to you. I thought you were about saying something. Winner. Audion Divine, what about you? Have you heard about center of gravity? No one is saying anything. If you can even hear me, just say hi. Let me be sure you can even hear me.
Hi.
Oh my goodness. So you guys are there and you don't say anything. No one is responding. You people are just there. You're not saying anything. Okay, that's fine. So let's move on. It means we don't know what it is. Now, center of gravity is simply defined as the point where the resultant weight of that body lies. The center of gravity is defined as the point in which the resultant weight of a body lies. So it is that point, it is the point in which the resultant weight of the body lies. So that is what, or let's use the word acts. Let's use the word acts, in which the resultant weight of the body acts. So that is what center of gravity is. It is the point in which the resultant weight of the body acts. Now, what does that even mean? Now, I can consider different objects. First of all, let me consider something that looks like this. Let's consider this to be a square. And I want to find the center of gravity, assuming this square is a uniform square object. And I want to find the center of gravity. The center of gravity is actually going to be at the center of this square. So the whole weight of this square will be at the center. How would I locate the center? If I draw a diagonal from one point to this other end, draw another diagonal from this point to this other end, this point of intersection, which happens to be at the center, assuming this object has a uniform what's it called, is a uniform material. It is uniform in the sense that it has an even distribution of mass. So we have masses distributed evenly across the whole body. It means that the center of gravity is going to be at the center, which implies that the weight of this object will be at the center of the object. If I have an object like this, let's assume this to be a beam, a uniform beam. Perhaps let's say the beam is 4 cm long. So this is my point 0 and this is 4 cm. Because this beam is a uniform beam, the center of gravity is going to be at the point 2, and the point 2 will be at the center of this beam, and that is where the weight of the object will lie. So anytime you hear that something is uniform, whenever you hear the word uniform in the question, what that means is that you have to take into consideration that the weight of the body is actually at the center of that thing they are telling you. So you can see questions like a uniform meter rule, a uniform beam. They'll give you the length. If it's a meter rule, they don't even need to give you the length because they expect you to know that every meter rule has a length of 100 centimeter, which equals 1 meter. And that is where the name meter rule comes into play. So if it's a meter rule, the center of gravity would be at the 50 cm mark of that meter rule. If it is a beam, they will give you the length of the beam. And when the length is given, assuming that once they mention to you that that beam is uniform, it means that the center of gravity, which is where the weight will lie, will be at the midpoint of that beam. And that is what this whole thing is all about. So it is the point where the resultant weight of the body lies. So take note of that. Okay. Now, the next thing we'll look at would be the condition for equilibrium of parallel and non-parallel forces. The condition for equilibrium for parallel coplanar forces. Let's write it that way. The condition for equilibrium for parallel coplanar forces. So we actually have, you need to understand what are even parallel forces. Can I do what? I didn't hear you. Say that again. I'm waiting for you. What did you say? I was thinking someone was about asking a question. Okay. All right, let's move on. So before we can look at the condition for parallel and non-parallel forces, we have to understand what are parallel forces and what are coplanar forces. So when we talk about coplanar forces, we are simply talking about forces that lie on the same plane. So don't look at it as something that is not a big word. Okay, so anytime you hear what coplanar forces, understand that coplanar forces are simply forces that act on the same plane. So forces that act on the same plane. While parallel forces can be likened to forces whose line of action are always parallel to each other. So in parallel forces, we see that their line of actions are parallel to each other. So take note, parallel forces are forces whose line of action is parallel to each other. Whereas that of coplanar forces, so coplanar forces are forces that act on the same plane. Are forces, okay, I've written that acts on the same plane. Now, take note of the fact that all parallel forces are always coplanar forces, but not all coplanar forces are parallel forces. So every parallel force can be called is actually a coplanar force, because for them to be parallel, they are actually on the same plane. But it is possible for something to be on the same plane and yet the forces are not parallel to each other. For example, now if I have forces, let's say I have a system of forces like this. I have this force. Let's say this is my point. Then I have another force like this, acting this way about this point. So this is my point P. And now I have, this is F2 and this is F1. So these two forces are actually coplanar forces. They are coplanar forces, but they are not parallel forces. They are coplanar forces because they are on the same plane. They are not parallel forces because they are not parallel to each other. So if I extend these forces downward, if I keep on extending them, you notice that they'll meet at a common point. They'll have intersection. But assuming the force is like this, where I have this one pointing straight, this one also pointing straight, then I have my pivot here. So my F1 and F2 are both coplanar force and also parallel force. So remember, in parallel force, we say that their line of action are always parallel to each other, whereas the coplanar force, they are just forces lying on the same plane. So now you might be asked to write the condition for equilibrium for parallel coplanar forces and non-parallel coplanar forces. So let's begin by parallel coplanar forces. Condition for equilibrium. So let me write that as a heading. So condition for equilibrium for parallel coplanar forces. Condition for equilibrium for parallel coplanar forces. So the first thing you have to know for parallel coplanar forces, the first condition is that the algebraic sum of the forces acting on the point in any direction is 0. So the algebraic force sum, the algebraic sum of the forces is equal to 0, or acting at that point, acting on the point. Let me add it up. Acting on the point equals 0. That's the first condition. So the first condition for equilibrium for parallel forces is that the algebraic sum for the force acting on the point is 0. The second one is that the clockwise, of course, this applies to both parallel and non-parallel. So the sum of the clockwise moment, is equal to the sum of anti-clockwise moments. So that is the second condition, that the sum of the clockwise moment equals the sum of the anti-clockwise moment. And the third one is that the total resultant force must also be 0. So the total resultant force equals 0. The total resultant force equals 0. So these are the conditions for equilibrium for parallel coplanar forces. Remember, we're talking about parallel coplanar forces. What if the forces are not parallel? What if the forces are non-parallel, but yet they are coplanar forces? How do we find what are the conditions? Now, just a little difference. Let me write that as a heading also. Condition for equilibrium. For non-parallel coplanar forces. Coplanar forces. So what are the conditions for equilibrium when the forces are not parallel? Now, for the parallel, we said that the algebraic sum of the forces is equal to 0. Now, in the non-parallel, we say that the vector sum of the forces acting on the body equal to 0. So the vector sum of the forces equals 0. And of course, you know the algebraic sum we mean is just to add them up the way they are. So you just add up the magnitude. But in the vector sum, we need to consider direction. Remember, anytime we talk about vector, direction is involved. So in that of the when they are parallel, so of course they're already in the same direction. So we just have to consider just sum them up the way they are. So you sum them up based on magnitude like that. But if they are not parallel, then we have to consider the direction at which they are inclined. Now, the second one is that, of course, I said that of moment applies, the principle of moment applies to every kind of forces, whether they are parallel, coplanar, or non-parallel. So the second one is that the sum of the clockwise moment is also equal to the sum of the anti-clockwise moment. So I'm going to use symbols in this case. Sum of the clockwise moments is equal to the sum of the anti-clockwise moment. And that's the second condition. Now, the third one is that the line of action of the forces must meet at a point. So the line of action of the forces must meet at a point. The line of action of the forces must meet at a point. Of the forces must meet at a point. And that is the three conditions for equilibrium, the third condition for equilibrium for non-parallel coplanar forces. And I think that is that for that. Okay, the last thing I would like to talk about, which I want to believe every one of you here should know, are types of equilibrium. Of course, we have three different types of equilibrium based on their position of rest. So we have the stable equilibrium, we have the unstable equilibrium, we have the neutral equilibrium, and I want to believe that doesn't sound strange to anyone right here. So let me see, write it. Types of equilibrium. Types of equilibrium. So under the types of equilibrium, we have stable equilibrium, we have the unstable equilibrium, we also have the neutral equilibrium. So how do we define these three types of equilibrium? Now, when we talk about a stable equilibrium, imagine having a funnel and then you turn the funnel upside down, like the round big surface is being dropped, is being put on the ground. Now facing the long mouth, the long nozzle, you've put it upward. Now that funnel is in stable equilibrium because if you raise the funnel up a bit and leave it, it falls back to its original position. So that is what stable equilibrium is all about. So we say a body is said to be in stable equilibrium if it tends to return to its position when slightly displaced. So I slightly displace it, I push it a little, it falls back to the original position where it was. It might not be at the same point, but the same way it was before, that is the same way it would be. So when it's slightly being displaced. But for unstable, the moment you touch it, it just also imagine you having like putting, let's say I have a bowl turned like this, and then I put a ball touch from the top of from this bow, you notice that it will roll far away from where the bow is. So we say in unstable equilibrium, a body is said to be in unstable equilibrium when it moves further away when it is slightly being displaced. So I slightly displace the object, then it moves further away from where it was before. Whereas that we said that when slightly displaced, it tends to come back to a new position. It will not move far away, but it will still move away a little, but comes to rest at a new position. So just take note of these three types of equilibrium.
Sir,
Are you with me? Can you hear me now?
Nope. Yes, I can hear you.
Where did you stop hearing me? Let me explain that.
I stopped at upside down funnel.
You heard that's a stable equilibrium.
Yes.
Okay, I said the stable equilibrium is a kind of equilibrium in which it tends to return back to its original position when it's slightly being displaced. And I use a funnel to give an illustration. So if I have a funnel like this, let's say this is my funnel. I'm not always good in diagrams, but let's say I have this is a funnel. So I try to put the funnel like this on the ground. So even if I raise the funnel up and it falls back again, it still returns back that original position. That is what we mean by stable equilibrium. But for unstable, which is this one I'm trying to draw here. So imagine dropping something like a tennis ball on top of a ball on top of a bow that is inverted. So a little push of that ball, the object is going to move very far away from where the bow is. Do you understand? And we call such kind of arrangement an unstable equilibrium. Whereas that of a neutral equilibrium, the body, when it is being slightly displaced, will come back to it. It will come to rest at a new position. So imagine that you put this funnel here, this funnel, you put it upside down, you just lie it with the body. You just lie the funnel with the body. So the nozzle is neither on the ground, neither is the base on the ground. So just lie it straight. So if you push it a little, it will just turn around, then comes to rest at a new position. That's an example of neutral equilibrium. So that was what I was trying to explain for these three types of equilibrium. And I'm sure everyone heard me on that. Did you all hear me?
Yes.
Okay. All right, so let's move on. So let's just continue with, let's try to see how we can solve problems using this principle of moment. The things I've explained are just basically some of the key things you have to know anytime you are dealing with the topic moment of a force. So let's see how the problems can appear and how do we solve them. So let's take the first question, question number 1. So these are examples under moment. So I have question number 1. So under question 1, the question says, a uniform meter rule balances on a knife edge. So we have a uniform meter rule balances on a knife edge. A uniform meter rule balances on a knife edge at 55 cm mark. At 55 cm mark. When a mass of 40 grams is hung from the 95 cm mark. When a mass of 40 grams is hung on the 95 cm mark. Now the question says Find the mass of the meter rule. So find the mass of the meter rule. So how do we find the mass of the meter rule? Now take down the question. I repeat the question just in case you can't see the writing so clearly. The question says that a uniform meter rule balances on a knife edge at 55 cm mark. I'm repeating the question. A uniform meter rule balances on a knife edge at 55 cm mark when a mass of 40 grams is hung on the 95 cm mark, full stop. When a mass of 40 grams is hung on the 95 cm mark, full stop. Now the question says, find the mass of the meter rule. Find the mass of the meter rule. So how do we solve this question? This question is very, very, very interesting. So how do we work it out? This is a practical question, and you should expect questions like this in your WAEC and even beyond, just in case you have other exams you're writing. Now, solution. So the first thing you have to do, are we all on the same page? Has everyone gotten the question? Let's be sure. Only one person responded. Okay. All right.
Yes.
Okay. So how do we solve this problem? First of all, you must take note that the question says that the meter rule is uniform. So I have to start by sketching the diagram. In this topic, if you can't sketch the question into diagram, believe me, you can't solve anything there. So your success begins when you can interpret the question into diagrams. So if you can sketch a diagram based on what the information given to you, then the solution is very, very, very easy. Some questions you will see, question one, sketch the information on the diagram. So they will they will add the diagram for you as one question on its own. Sometimes it comes like that. Now, let's go straight and solve. Understand, let me sketch a line diagram. Let this line here mean my meter rule. And of course, a meter rule has from 0 to 100 cm. The length of a meter rule is 100 cm. So that first point is 0.0, and then the other point is my 100 cm. And now they said that the meter rule balances on the knife edge at the 55 cm mark. So let me put my 55 cm mark to be somewhere here. It doesn't need to be exactly at where it should be. Just anywhere, anything you call your diagram, that is what it is. So for me, this is my 55 cm mark. And that is where the meter rule balances. And they said that this meter rule balances here at a condition. Remember that normally every uniform meter rule should balance at the center. Is that not true? The center should be the point where the weight of that body should be acting. Do you understand that? So it means that normally that this meter rule should have, let me try to sketch the diagram. Let me take the beam a little bit further. Before I even draw that pivot, let me explain something I missed. Now notice they told us that the question that the meter rule is a uniform meter rule. And because it's a uniform meter rule, the center of gravity for the meter rule is going to be at the midpoint of this meter rule. And the midpoint of this meter rule is where the 50 cm mark. That is actually where the weight of the meter rule will be acting upon. So I have to identify a point, 50 cm. So let this point here be my 50 cm. This is my 50 cm. And that is where the weight should be acting. So let me draw a weight. Let me call this line my weight, W. But they now said that other than that the meter rule balanced at 55 cm mark. So I have a 55 cm mark somewhere here. So this is my 55. And they said that the reason why this meter rule balanced at this 55 cm mark, according to the question, they said that a mass of 40 grams is hung from the 95 cm mark. So this is 100 cm. Let this be, this is my 95 cm mark here. So this is my 95 cm. And on this 95 cm, a mass of 40 grams was being hung there. So this is my 40 gram mass. And of course, this 40 gram is going to exert a weight that is acting downward. Now, recall, if I don't think I mentioned that. Moment of a force, the unit for moment of a force is Newton meter. Newton meter. So anytime you are dealing with anything that has to do with moment, you have to make sure your conversions are in this unit. You must make sure that your force is in Newton and the distance is in meters. It is very accurate doing it like that. Even though unless you are solving for distance, and since the meter rule already is given in cm, I can choose to solve for my distance and get the value also or in cm. But since the question says I should find the mass, and of course mass is measured in kilogram, I have to ensure that anything I'm dealing with, I should work with a standard unit for moment. So let that not confuse you at all. Now, I was given a mass of 40 grams. Before I can know the weight of this body acting downward. Now, how do we know weight? If you're giving mass, remember weight is equals to mass times acceleration due to gravity from your elementary physics. So if the mass of 40 grams is there, what then is the weight? The weight becomes 40 multiplied by 10. Is that correct? Where are you confused? I'm listening. Ask your question. At what point are you confused? Okay, let me recap again. Now, we are trying to put the information they gave to us into diagram. Now, the question told us that a uniform meter rule. Now, notice that this meter rule, this line I drew here is my meter rule. And every meter rule has a length of 0 to 100 cm. Remember, I also told you that once you have something that they said uniform, if they say uniform beam, uniform meter rule, once you start hearing that word uniform, it means that the center of gravity is going to be at the midpoint of that very object. And in this case, the midpoint for 100 cm is going to be 50 cm. That is, when I say midpoint, I mean the center. So the center of something that is 100 cm long is actually at the 50 cm long, 60 cm mark. And that 50 cm mark, that is where the weight of the body would be. That is why you saw me put this thing W at the 50 cm mark. Do you understand? That's the first thing. Now, but I'm sure do you understand that one? Can you please respond to me? Do you understand that? Someone said I don't understand. You don't want to respond to me. Who said I don't understand before? Yes. What exactly is yes? Okay. Let's go back to the question. So, from what I was saying, I've drawn my 100 cm, which happens to be the length of the meter rule, and the center of gravity, which is at 0.50, that is where the weight of the meter rule is going to lie. That is why you see me label here, weight. And the weight is actually at 0.50. That is where the center of gravity lies. And because this meter rule, they said that the moment they put a load of 40 grams at the 95 cm mark, this is my 95 cm mark here. So the moment they put that load of 95 or 40 grams at that 95 cm mark, they now said that the meter rule balances at 55 cm mark. So it means that if I put a point of balance here, this pivot is called a knife edge. If I put a knife edge at 55 cm mark, this thing here, this meter is going to be balanced. That's what they are telling me, based on the fact that I hang a load of 40 grams at the 95 cm mark. That's the question. Now they asked me to find the mass of the meter rule. That's all. So how do I even find the mass? Before I can do that, I have to find the weight on this 40 gram. What is the weight? Remember that weight is mass times acceleration due to gravity, and acceleration due to gravity is a constant 10 meters per second square. So meaning that if I multiply the mass, which is 40, by 10, I would then get the weight. So what is 40 times 10? That would give me 400 Newton. So 400 Newton is actually the weight of this 40 gram. But I need to convert, sorry, not 400 Newton, please, because I've not converted mass to kilogram. Remember, Newton is a product of, you have to convert your mass to kilogram and then convert also your, before you can convert the weight to Newton. So if I convert 40 gram to kilogram, how do I achieve that? I have to first of all divide the 40 gram by 1000. That is how you convert from gram to kilogram. Anytime anything is given to you in grams, you want to convert it to kilogram, you have to divide that thing by what? 1000. And if I divide 40 by 1000, I will get 0.04 kilogram. So that is the mass of this object in what? Kilograms. So if I multiply 0.04 by 10, which is the acceleration due to gravity, it means that the weight of this body is going to be 0.4. So that is actually the weight of this 40 gram mass on this arrangement. So 0.4 Newton is acting as a result of what? The 40 gram being hung on the 95 cm mark. Now, the next thing we have to take into consideration is the distance from the knife edge down to where the mass is being hung. Now, notice that, how do we get the distance here? This point is 95. This other point is 55. So you check, what is 95 minus 55? That will give us what? 50. Sorry, that will give us 40, right? Yes, 40 plus 55 is 95. So this place here is going to be 40 cm. And if I convert 40 cm to meters, how do I do that? 40 divided by what? 100. That would give me 0.4 meter. So I just want my conversions to be in standard unit. I don't want to work with anything that is not standard unit, which is very, very safe and very, very important. All right, that gives you that makes your answer to be in unit that is actually standard. Okay, so also if I consider the distance from here to this point here, what will be the distance? The distance is actually this 55 cm mark, which is where the pivot is, minus the 50 cm, which is where the weight lies. So 55 minus 50, that would give us 5. And 5 converted to meter means 5 divided by 100. And that would give us 0.05 meters. So which is the length from where the weight is lying to the pivot. So on this note, I can now make use of my principle of moment to answer the question. So using the notes, using that, remember, this is my clockwise, this is my anti-clockwise, and according to the principle of moments, we have that the sum of the clockwise moments is equal to the sum of the anti-clockwise moment. That is what the principle says. Now, what is moment? Recall that moment is simply force times perpendicular distance. But moment, recall that moment M is equal to force times the perpendicular distance. So if I consider the clockwise, which is, we have a force of 0.4 Newton here, and then we have a distance of also 0.4 meters. So if I multiply 0.4 Newton by 0.4 meters, that gives me the clockwise moment. So I will have that. It implies for my clockwise moment, 0.4 Newton, which is the force, multiplied by 0.4 meters, which is the distance, is going to be equal to the anti-clockwise moment, which is the weight, this weight here, W, multiplied by the distance from the weight to the pivot, which is 0.05. So if I multiply the weight W times 0.05, so the weight, which is the force, multiplying 0.05. And if I multiply 0.4 times 0.4, that will give me 0.16. And then W multiplies 0.05 will give me 0.05 W. And then how do I get W? I have to divide both sides by 0.05. And if I do that, my W becomes 0.16 divided by 0.05. And I would want someone to tell me what that value would be. So what is 0.16 divided by 0.05? Please, someone must have to respond. I want you guys to respond.
3.2.
3 point what?
2.
So we have 3.2. So it means that the weight of that body is actually 3.2 Newton. Sorry, that is the weight of the meter rule, 3.2 Newton. But they didn't tell us to find the weight. They asked us to find the mass. But I know that weight, W weight is equal to mass times acceleration due to gravity, G. So this means that weight, which is 3.2, is equal to the mass, which is unknown. Acceleration due to gravity is constant, which is 10 meters per second square. So that, therefore, my mass, which is M, is going to be 3.2 divided by 10, and that will give me 0.32 kilogram. And that is the mass of the meter rule. And that is what the question is trying to ask us to do. Now, I will encourage you, after the class, you might not understand everything now, but if you go back to the video, which will be posted before the day runs out, from now to the early hours of tomorrow, the video will be uploaded on the site. So you can always go back and make reference. Just go back, check over and over again. This thing is, once you understand how the diagram is being drawn, if you understand this diagram here, then you can literally understand every other thing, because every other thing becomes easy the moment you understand how to sketch the diagram. And that is how it is. So ask me your question before we move to the next question. We don't have as much time. Someone should ask question. In the next 5 seconds, if there's no question, we just move on to the next thing.
Sir, please, can you raise the screen up? I'm writing the question. I'm writing it.
Okay.
So I'm not seeing your screen.
You're not seeing my screen? Did you say you're not seeing my screen?
Yes, I'm not seeing it.
Please hold on. Wait. Why is the screen stuff not? Can you see the screen now?
Yes, sir. Oh, he has gone back.
Are you done writing to this point?
Yes.
So any question before we proceed?
Sir, the
Okay, no.
question.
Okay, I'm listening. Ask me your question.
50 same came out.
The 50 watts cm on the diagram,
Yes,
the 50 cm, that's this midpoint. Remember I told you that
yes,
the center of gravity of every object should be at the center of that object if the object is a uniform object. Now the question told us that the meter rule is uniform meter rule. So it means that the weight of the meter rule will be at the center of that meter rule, which is the 50 cm mark. And that's why you saw that I put W at the 50 cm mark. Does it make sense? You didn't respond again. It doesn't make sense.
Sir, how did you get 100?
100 is the total length of the meter rule now. The
Oh,
meter rule is 100 cm long. So once you hear meter rule, the length of a meter rule is 100 cm. Do you understand?
yes,
So every meter rule has a total length of 100 cm. So it means that the center of 100 is what? 50. Is that not true? So
yes,
the weight of the meter rule will actually be at the 50 cm mark. That is why you saw me put W here. Do you understand? And
yes, sir.
every other information I have on the diagram is as it is given in the question. So they told me that they hang a mass of 40 grams at the 95 cm mark. So I have to locate a point where I called 95 cm mark and I put the mass there. And they told me when the mass was being hung, that the balance point of the meter rule was found to be 55 cm. That is why you saw me put this pivot at the 55 cm. I'm the one locating my point. So anything I call those points, that's what they are based on the question. So the pivot, this triangle here is actually my knife edge or pivot that represent the point of balance of the meter rule when the mass was being hung. So they asked me to find the mass of the meter rule. So for me to find the mass of the meter rule, I needed to know the weight first. This weight here, remember they didn't give me the weight. So I need to know the weight first. And the moment I found the weight using the principle of moment, that's what you saw me do here. That the
Yes,
clockwise moment is equal to the anti-clockwise moment. And what is the weight? The clockwise moment is this force here, 0.4,
yes,
multiplying the distance 0.4. Do you understand that?
yes,
So after I did that to get the clockwise, then I also consider the anti-clockwise, which is the weight W multiplying the distance 0.05. Do you understand that? So
yes,
that gave me the anti-clockwise. Since moment is first time distance. So when I multiply 0.4 and 0.5, I have 0.16, and then this gave me 0.05 W. If I make W subject, I divided both sides. I now have that 0.16 divided by 0.05 gave me 3.2. And
yes.
since the weight is 3.2, I know that weight is mass times what? Acceleration due to gravity. And that was what I did here. What is the weight? 3.2. The mass is unknown. Acceleration due to gravity is constant. They don't need to give you. You have to know it. It is always 10 meters per second square unless they give you otherwise. It can be 9.8, 9.81, but always use 10 when it's not given. So if I divide 3.2 by 10, I will not get the mass, which is 0.32 kilograms.
Okay.
Does it make sense now?
Yes.
Okay. So now let's take one more question. The questions are usually interesting, like this. I would have taken more than that, but let's try to see how to take just one more question based on what we have. And I'll take something exactly similar to this, so it doesn't throw us off balance. But the questions can actually take any form, all right? But anyhow it looks like, always use the principle of moment to tackle the question. So this one says, that a meter rule is found to balance at the 51 cm mark. Now, notice they didn't tell us that this one is a uniform meter rule. So, question 2, they said a meter rule is found to balance at the 51 cm mark. They now said when a body of mass 70 grams is suspended at the 10 cm mark, when a body of 70 grams is suspended at the 10 cm mark, they said that the balance point is found to be 25 cm. The balance point is found to be 25 cm. Now the question says to be 25 cm mark. The question says we should find also the mass of the meter rule. So you see, this is another WAEC question, and they ask us to find the mass of the meter rule. Now, this question actually has a big part. Maybe on Friday, our next class will still try to repeat this topic and solve other questions on it, because it's a very important topic as long as WAEC preparation is concerned. Okay. Meanwhile, I said Friday. Today is Friday. I mean on Monday, please. On Monday, not Friday. Okay. Is that on Monday or even Tuesday? I don't even know what I'm saying again. Did you get the question before I start solving it? Did everyone get the question? Let's say something now.
Yes.
Only one person got it. Okay. You can always go back and check it. Now let's solve the question. Now, solution. So we start by sketching our diagram. So let's sketch our diagram. This is my meter rule. This line I drew here represents my meter rule. And they say the meter rule is found to balance at the 51 cm mark. So that 51 cm mark, that initial 51 cm mark, let me call here my 51 cm mark. So this is my 51 cm mark. Wait, let me check where I will call it at the 10 cm mark. Okay. Let the 51 cm mark be somewhere here. So this is my 51 cm mark, and that is where the weight of the body is going to lie. So this is my W. Why am I putting it here? Because the question told me that the meter rule is found to be balanced at the 51 cm mark. That's the first thing. So that 51 cm mark is actually where assuming there is no mass attached to this meter rule, this 51 cm mark will be the point of balance for this meter rule. Remember, a meter rule has a total length from 0 to 100 cm. So it means that the distance from this 0 to this point is 51. So from 51 to 100, the distance is 49. Take note of that. Okay. Now, they now said when a mass of 70 grams is hung on the 10 cm mark. So the moment I put a mass, this is let here be my 10 cm. So the moment I put a mass of 70 grams here, so 70 grams, they said that the moment I had this, that the balance point is found to be 25 cm mark. So the meter rule now came to balance. at 25 cm mark. So this is my 25 cm mark. You see that? That's where the pivot will lie. Now the question says I should find the mass of the meter rule. Before I can find the mass, let me get the weight as a result of this 70 gram mass. So what is the weight? First of all, if I divide 70 by 1000, that is how to convert from grams to kilograms. Divide 70 by 1000, that would give us 0.07. Then I have to multiply the mass by acceleration due to gravity to get the what? Weight. And that is 0.07 multiplied by 10. That will give me 0.7 Newton. That is the weight of this meter as a result of this 70 gram mass. So the weight that will be there is going to be exactly 0.7 Newton and it's pointing downward. So I've gotten the weight here.
I'm not seeing your screen.
Hey, what's going on now? Why is the screen? Why does it keep going off? Screen is still being shared. Does anyone still not see my screen?
Yes, me.
Oh well, let me reshare. What about now?
Yes.
Yes.
Okay. Okay, so this is the diagram as I was trying to illustrate, as I was trying to put down according to the question. So I've been able to draw the meter rule. Then they said that the meter rule was found to be balanced at the 51 cm mark. You can see at the 51 cm mark, I put my weight there. That's what you see me do here. That is where the weight is actually going to lie. So that weight, they now told me that the moment they bring a mass of 70 grams, this mass of 70 grams, they now said when they put it at the 10 cm mark, which is here, that the balance point is found to be 25 cm mark. And that 25 cm mark is where the pivot is going to be. You see that? So I have to convert this 70 grams to know the weight. I converted 70 by to kilogram, 70 grams to kilogram by multiplying it by 1000. And when I did that, I got 0.07. And when I multiply 0.07 by acceleration due to gravity, which is 10, I then got 0.7. That is the weight of this 70 gram mass. You see that? So the question now says I should find the mass of the meter rule. So meaning, just like we did before, I need to know the weight first. When I know the weight, I can now find the mass. So what do I do? Let's find the distance. So from here to where the pivot is going to be 25 minus 10. And 25 minus 10 will give us 15 cm. And 15 cm, if you convert 15 cm to meter, would be 15 divided by 100, and that will be 0.15. So that will be 0.15 meters. All right. Also, the distance from this 51, from the 51 where the weight is down to the pivot, the total distance there will be 51 minus 25, and that would give me 26. And 26 divided by 100, which is converting it to meter, that will give me 0.26 meters. So that is the distance from this way to the pivot, and then from the other way to the pivot. So remember that the sum of the clockwise moment is going to be equal to the sum of the anti-clockwise moment according to the principle of moment. All right, so let's use that analogy and solve the problem. So according to the principle, we know that the sum of the clockwise moment is equal to the sum of the anti-clockwise moment. So it means that, and you know that moment, when we say moment, will mean force multiplied by distance. So if I consider the perpendicular, the clockwise motion, the weight, which is the force here, multiply the distance, which is 0.26. That is for the clockwise. So this implies that weight W multiplying 0.26 must be equal to the anti-clockwise moment, which is the weight here, 0.7 multiplying 0.15. So if I do that, that will give me 0.7 multiplying 0.15. Of course, if I want to find W, first of all, this will give me 0.26 W. What is 0.7 multiplied 0.15? Please, somebody should confirm that for me. 0.7 multiplied 0.15. Someone should respond now. I'm listening.
0.105.
0. What?
105. 0.105.
10 what?
0.105.
105. Okay. So 0.105. So if I divide both sides by 0.26 to find the weight, so the weight becomes 0.105 divided by 0.26. So what is 0.105 divided by 0.26? Let's find the weights. What would that be? Please, someone should respond now. 0.105 dividing 0.26. What would that give us?
0.4038.
So
Should I?
0.404. Let's leave it at 3 decimal place. 0.404 Newton. So that is the weight of that, approximately 0.404 Newton. I heard that. So since
Yes.
we found the weights, we can now find the mass. So, but weight, W, is equals to mg. So it implies that my 0.404 is going to be equals to what? The mass multiplying acceleration due to gravity, which is 10. So if I divide the both side by 10, it means that the mass becomes 0.404 divided by 10. And that will give me 0.0404 kilograms, which is actually the mass of that meter road. And that is how to answer that question. So you see that this principle is the same. Just know how to sketch your diagram. Once you can know how to sketch the diagram, every other thing becomes as easy as ABC, just like you've seen me do. So where are you writing? Let me take the screen to there. Have you written down everything?
Nope. Starting from the top.
From the top. Have you drawn the diagram?
I give this. Oh.
Sorry about that. Are you still drawing the diagram?
Sir, please raise the screen up. Okay, sir, raise the screen. Okay.
Okay, so that is that for the principle of moment. Now, what will happen is that in the next class, we'll try to solve more questions on this, and possibly we still solve another some other questions on the last topic. So the next class will just be a kind of more practical questions on the simple AC circuits and also that of the principle of moments before we proceed to the next topic. Or do we just move to the next topic since we understand this one? I would want us to decide.
Yes.
We should proceed to the next topic, right?
Yes.
Okay. Okay, that's awesome. So what you do for me is that, so always go back, just in case you're confused at any point, just go back to the video, try to solve questions on your own, try to practice. Everything is as simple as ABC, so nothing is difficult. And this is where we'll bring it to the end of the class. So I ask again, does anyone have any question before we take attendance?
Sir, this last question we did, can I get the question?
Okay, I will add it up to the assignment this thing. So just check the assignment, you'll see the question. I'll post it on the assignment space. So if you
Okay,
check
sir.
the assignment page, you'll see the question.
Okay.
Okay.
Yes, sir.
All right. So we have Omaomi, we have Melody, Obaomi, Melody, and Victoria.
Yes,
Okay.
sir.
Right. So that is all for now. See you all in the next class. Do have a good night, right?
See ya.
All right.
Yeah. Next, next student. Next student. First
Mm, mm, mm. And Manuel is should start with one subject.